Hello, year 13. Okay, so basically I've set you this paper, paper Q, and the answers are at school, and I'm currently isolated, so I can't actually get the answers. So I'm just going to have to do it the old way. If you want something done properly, do it yourself. By the way, yeah, I haven't been able to. Well, basically, I've been put. The way we've done it in the maths department is we've divided up the work between us for different year groups, and I've got year 12s at the moment, so I've been setting work for them. But I'd quite like to add plenty of stuff for you because and I'll be doing it in the same Google Classrooms that we normally use. So keep checking there. I just put it like this. Whilst you're not going to do an exam, which to be honest breaks my heart, it really does. I think it's much better if you do an exam. It's just a better way of doing things. But they've cancelled them for their own reasons, obviously. I just don't want you to get out the habit of doing mathematics because many of you are going to be doing mathematics at university or a closely related subject, and you're going to be needing this math. So by all means, keep practicing on the papers. You've got plenty of time at the moment. You're in quarantine, so you might as well do something. Keep working on your maths. I can set as well lots more kind of interesting problem solving kind of mathematics, and yeah, we can do some interesting stuff. Anyway, so here is paper Q. We've got 6 over 4x squared plus 8x minus 5 plus 3x plus 1 over 2x minus 1, and we want to write it as a single fraction in its simplest form. Now, it's always the same trick really with these ones. You really should try and factorize. This looks like a quadratic, which is going to factorize nicely. And I tell you what I think on these ones. It's very likely that one of the factors is going to be the same as what's on the bottom of the right hand side, 2x minus 1. So let's give that a go. Is that going to work out, 2x minus 1? I'm hoping basically that would mean that would have to be 2x plus 5, and that gives me 10x minus 2x. Yeah, it works. It works. Like I say, that was just like a hunch, really, a guess that 2x minus 1 would be one of the factors, and sure enough, it was. Now we can obviously times top and bottom of this one by 2x plus 5, and it will be the same value. And then we can just simplify at the end, and we've got a common denominator now. So let's just make that like that. It's a bit cheeky, that move. I can do it. Obviously, I'm on a whiteboard, but yeah, that's a good idea. So then we'll have 6 plus, looks like 6x squared, plus 2x plus 15x, so that's plus 17x, and then plus 6, all over 2x minus 1, 2x plus 5. And you should really just check that nothing else factorizes at the end, and that's why I'm doing this extra work. It may well not, but let's have a look. Okay, I get 6x squared plus 17x plus 12. Over 2x minus 1, 2x plus 5. Now, my next bit of factorizing is only important if it's going to cancel. And, there's a chance it might factorize and cancel. We've got 6x squared plus 17x plus 12. We could try, let's see, a 6x and an x. A sort of cheeky way of doing this is by checking on your calculator for nice solutions. So if you get your calculator out and get it to solve that quadratic, if it has nice roots and nice solutions, then you know it factorizes. Being the lazy maths teacher that I am, that's exactly what I'm going to do now. So polynomial, degree 2, 6, 17. I should really know this in my head, but I'm useless, aren't I? It does have nice roots, and there we go. It's actually 2x plus 3, and what was the other one? 3x minus 4, 4x, 3x minus 3x plus 4. So let me just scribble that out. It does factorize nicely, but I don't think it's actually going to simplify, which means that it was actually quite unnecessary, but there we go. It's always good to check, isn't it? So 2x, 3x, I think it's going to be plus 3 and plus 4, and I think that gives you the 8x plus 9x, 17x, yeah. But nothing cancels there on the bottom, but we have at least left it in a nice format, and you're good. Yeah, but we can't cancel anything at the end. Let me know if I've made a mistake, obviously, in the comments. I'm sure you will, but yeah, that's what I make question 1. Okay, so let's go and do question 2. Now, where's what do I select up here for a new blank board? Here we go. Delete. Create new board. Oh, but actually, let's just delete the old board. delete. Yes, delete the board. Leave page. Start drawing. Okay, so question 2. What we got next? We've got a pattern out of some squares. First 3 patterns shown below. It seems to be going 5, and then 1, 2, 3, 4, 5, 6, 7, 8. Is that right? Let me just check. I've added those up. It's early in the morning. And I've got 5, 6, 7, 8, 9, 10, 11. So looks like the sequence 3m plus 2. Is that the first question? Yeah. It's very much looking like the sequence 3m plus 2. And you can, I mean, like, you could prove as well that that sequence is 3m plus 2, because you're always adding, if you look at it, the way it's generating those squares, you're adding, you've got 2, then 4, then 6. That's why you've got plus 2 essentially, but then you've got 3, 4, 5. Yeah, we're doing 3. Yeah, well, you can just find an expression and write it down. It's pretty obvious it's 3m plus 2. Okay, so that's the first bit done. And that bit's just like GCSE, really. Jacob uses a total of 948 squares in constructing the first k patterns. So this is a sum of an arithmetic sequence, yeah? And the sum of an arithmetic sequence is given by Sn equals n over 2, 2a plus m minus 1 times d. And we're doing 948, so we've got 948 squares, and that is, and k is representing n here, so k over 2. A is 5, so we're going to have 10 there, and then we're going to have k minus 1 times the difference, so we're going to have 3 times k minus 1. Sorry, I've put the d on the other side of the brackets there. Now it's just a case of rearranging. I suppose I better times 948 by 2, and I've got a hunch that it could be 1,896 because it's in their answer. And then I can do 10k plus 3k squared minus 3k, and I've done a lot of that in my head, but it should be all right. I hope you get it. And then you've got the answer basically. 0 equals 3k squared plus 7k minus 896. And it's a bit of a shame that they didn't ask you to solve that. You could have just done it on a calculator, I suppose, but there we go. Missed opportunity for them there. Okay, let's do question 3 now. I think I'll just go down on my board actually for question 3. Question 3. What have we got here? We've got g of x is 3 sine of x over 6 cubed minus x over 10 minus 1. So a horrible looking function, maybe used for modelling or something like that. We've also got a restriction on x, minus 40 to 20. Okay, and x is in radians. Radians. I'll put a little c there to remind myself that it's in radians. Okay, we've got looks like a fixed point iteration question. We've got to show that if this equals 0, it can be rearranged to give the rearrangement in the question. Yeah, and it's going to be exactly, by the look of it, how you'd guess to rearrange this, minus x over 10 minus 1. So I'm going to add the x over 10 and the 1 first. So I've got x over 10 plus 1 equals 3 sine x over 6 cubed. Now look where you're going here. They've got x over 30 and they've got a third, so we want to divide by 3 next. And I tell you what, let's also do the arc sine as well straight away. And then we've got x over 6 cubed. And then we want to cube root and times by 6, just as they have done. So it's exactly how you would have expected this one to be done, really. And we've shown that that is the case. I'm sure that wasn't really any stress for you. Cool. Okay, and part B. Okay, what do we got here? Using the formula, find values of x1, x2, and x3. Well, this is fast calculator method, isn't it? This is like fixed point iteration. So I'm going to get my calculator out. I've got it right next to me. I'm going to type in, what's their starting value? 4, and press enter. And then I'm going to type in that incredibly long formula into my calculator, making sure I'm in radians. Easy to not be in radians there. Okay, I'm in radians now. And so what have we got? 6, open bracket, inverse sine of x over 30, or answer over 30, I should say. I try and use brackets very carefully when I'm typing these in. Answer over 30 in its own brackets plus a third, close bracket, and then close another bracket and power of a third, I think, to the power of 1 divided by 3. Okay, and I press enter. I get 4.71 for x1. I'm going to check these as well at the end because it's very easy to check your answer. And it's a shame, actually, because the question doesn't ask you to do it, and it could do. They want to like 3 decimal places, don't they? 0.716. x2, I just press equals again once, and I get 4.802. And x3, I press it again, I get 4.812. And at the end, just to check my answer really, because you know I'm a big fan of checking answers, I'm just going to press it a few more times. It seems to settle around 4.8139. I'm just going to write that down, 4.8139. Now that's saying that if I plug it into the original equation is this equation here, it should solve it. It should be really, really, really close to 0. So let's just type in 4.8139, press enter, and now I'm going to do 3 sine of my answer divided by 6, but I'm going to cube that. And I'm going to put it in brackets because I never know if calculators, I presume they do sine functions after cubing, but I like to put in brackets just in case. There we go. Because that's the order it's done in. Minus answer over 10 minus 1. And I press enter, and I get a number which is 0.0000271. Sounds right to me because it's so close to 0. So that was just my little check. Okay, question 4. What do we got for question 4? We've got when theta is small. Okay, when theta is small, and it's a show that question. So show that question is always quite good fun. Because you know whether you've got the answer right. That's why I quite like them. So we've got 1 plus sine theta plus tan 2 theta over 2 cos 3 theta minus 1. And we're essentially, let's use some limits just to be showing off really. The limit as theta tends to 0. That's really what we're saying. Because as theta tends to 0, sine theta tends to theta, and really the question should be much more carefully worded. They should say when theta is small enough for 3 theta to be considered small, but they don't because they're at XL and they do these kinds of things. But yeah, anyway, all we've got to do is remember our small angle formulae. Sine theta roughly equals theta, tan theta roughly equals theta, and cos theta, only difficult one to remember, 1 minus theta squared over 2. Okay, so what do we get? We're going to get 1 plus theta plus 2 theta over 2 minus theta squared after you've times that by 2. It's 3 theta though. So let's make sure 3 theta is in brackets squared minus 1. And that is the limit as theta tends to 0 of 1 plus 3 theta over, what is that? That's going to be 1 minus 9 theta squared, and that's difference of 2 squares on the bottom. The limit as theta tends to 0. You may not be used to writing down limits constantly in these, and they wouldn't mind, that's fine. 1 plus 3 theta, 1 minus 3 theta. And they cancel, leaving the answer 1 over 1 minus 3 theta. Whilst theta is small, I'll just write. And that's it. That's all you need for a small angle formulae question. They're pretty straightforward. Now, hence write down the value when theta is small. This is when the limit notation comes in, yeah? This is why I was writing it down in terms of limits, because whilst theta is very small, yeah, it's tending towards 0. And what happens to 1 over 1 minus 3 theta when theta is tending towards 0? Well, it becomes 1 over 1 minus 0, which is essentially 1, yeah? And so the limiting value is 1. Okay, I'm just going to do one more question on this video, and then I'll do the next 5 questions on a separate video just to break up the size of the files. Okay, question 5. Another arithmetic sequences question. Let's have a look. Prove that the sum of an arithmetic sequence is that. Okay, so this is classic, this one. For any arithmetic sequence, let's call the first term A. The second term will then be A plus D. Yeah, and we're doing a sum as well. So sorry, let me just turn that comma into a plus. And so that's the first term, that's the second term. And this is going to be the sum of the first n terms. Note the third term is going to be A plus 2D. And the fourth term is going to be A plus 3D, ... Well, what about the nth term? Well, notice the first term is 0D, the second term is 1D, the third term is 2D, the fourth term is 3D. And so the nth term, yeah, so this is the nth one, is going to be A plus not ND, but M minus 1D, because what you times D by is always one behind the term in the sequence, and so that is the sum of the first n terms. Now the trick is to consider this written down backwards. If I had the last term first, then that would be A plus M minus 1D. The next term would be A plus M minus 2D. And then let's just put ... And then right at the end, you're going to just have a plus A. Now, what happens when you consider adding each of these terms to themselves written down in backwards order in the sequence? Well, if we added these two equations, we'd have two SNs, but each term would add up to exactly the same thing. Now, what is A plus A times M minus 1D? It's 2A plus M minus 1D. What about the next term? Well, A plus A is still 2A, but if you've got M minus 2Ds and you add another D, that will give you N minus 1Ds in total. So you've got exactly the same thing. And that's the trick. Essentially, you get exactly the same term each time, all the way up to the last term where you're still getting 2A plus M minus 1D. Now, how many terms are there? Well, there are now n terms. And so we could simplify this to 2Sn equals n times 2A plus M minus 1D. And then you can just divide by 2 on the n, and you've got their answer as required. So you can just put as required at the end. And that is how you prove the sum of an arithmetic sequence. It then wants us to, in part B, find the sum of the first 200 odd numbers. Okay, so we're going all the way up to, and we're only doing odd numbers, aren't we? So we're going up to 199, yeah? Now, notice that is the 200th number in the sequence, because this is a sequence 2n minus 1, and 2 times first 200 odd numbers. Oops. So it should be going up to 399. That would be the term 2 times 200 minus 1. And that would be the first 200 odd numbers, because the odd numbers are the sequence 2n minus 1. Yeah? And so that's how I know that the last term is going to be 399. Okay, so how are we going to do this? We're going to do the sum equals number of terms, 200, over 2. 2 times the first term, which is 2, plus m minus 1, well, that's 199, times by the common difference, which is 2. And then you can just get your calculator out, or even do this one in your head. That's going to be 398 plus 2, 400, times by 100, which is 400 with 2 zeros on the end. Sorry, it's too early in the morning to get 40,000 out of my mouth, but I believe that is the final answer. Okay, that completes the first 5 questions. Hope you are clear on everything, and yeah, best of luck with how you're getting on.